The story of how astronomers found ASKAP J1424 begins with a remarkable piece of technology sitting in one of the most remote places on Earth out in Western Australia, where the landscape is dry and largely empty. Sits the Australian Square Kilometre Array Pathfinder, or ASKAP for short. It is not a single telescope, but rather an array of 36 separate dish antennas, each one about 12 meters across, spread across the red desert floor. ASKAP was built as a technology demonstrator, essentially a testbed for the much larger Square Kilometre Array that will eventually span multiple continents. But this smaller cousin has already proven itself capable of making discoveries that larger, older telescopes simply cannot match. The secret lies in how it sees the sky. Traditional radio telescopes have a fairly narrow field of view, like looking through a paper towel tube. ASKAP uses something called a phased array feed system, which is more like having a wide-angle lens. Each antenna can capture a patch of sky about 100 times larger than previous instruments could manage. This wide field capability makes ASKAP perfect for large survey projects. One of the most ambitious is the evolutionary map of the universe, known as EMU. The project's goal is straightforward, but enormous. The researchers want to map the entire radio sky in unprecedented detail, cataloging tens of millions of galaxies and other cosmic objects. What makes EMU particularly useful for finding strange objects like ASKAP J1424 is how it observes. The survey uses long dwell times, meaning it stares at each patch of sky for extended periods. Rather than just scanning quickly, it also returns to the same regions repeatedly with high cadence. This approach is ideal for catching things that pulse or flicker on timescales of minutes to hours exactly, the range where long-period radio transients live before ASKAP and surveys like EMU, that middle ground between fast pulsars and slow variable stars, was largely unexplored territory. On January 9, 2025, something unusual appeared in the data from one of ASKAP's observation runs. The team was conducting a circular polarization search as part of their standard processing of scheduling block, SB7271. This particular observation lasted about 10 hours, and buried within all that data was a signal that did not match anything the researchers had expected to find. What they had detected was pulsed radio emission, but the timing was strange. The pulses arrived with a period of 2147.27 seconds, which works out to roughly 36 minutes between each one. That is an extraordinarily long interval for any kind of regular astronomical pulse. Most known pulsars spin dozens of times per second. Even the slower ones might complete a rotation every few seconds, but 36 minutes that placed this object in a category that barely existed. The discovery prompted immediate follow-up observations. The team turned to the Australia Telescope Compact Array, known as ASKA, to watch the source more closely. For 8 consecutive days they tracked it, and for those 8 days the signal remained remarkably consistent. The pulse profile stayed stable. The timing held steady. Whatever this object was, it was behaving in a predictable, repeatable way during that entire window. Then something changed after those 8 days of activity. The source simply went quiet. The pulses stopped arriving. It was as if someone had flipped a switch. The object that had been broadcasting its 36-minute rhythm just faded back into the background, leaving behind nothing but questions and a dataset that would keep astronomers puzzling for months to come. One of the most striking things about ASKAP J1424 is what happened when astronomers looked closely at the polarization of its radio emission. This turned out to be unlike Almost anything researchers had seen before the signal was 100% polarized across the entire pulse profile. That is unusual. Most radio sources emit a mix of polarized and unpolarized light, but ASKAP J1424 sent out a completely polarized signal every single time it pulsed. But the story gets stranger. The polarization was not static. It changed character. As the pulse progressed, it started out elliptically polarized, which means the electric field vector traces an ellipse as it oscillates. Then, over the course of each pulse, the emission transitioned to become fully linearly polarized. This was not random behavior. When the researchers plotted these changes on something called a Poincaré sphere, which is a mathematical tool for visualizing polarization states, the data traced out a well-defined great circle path. Think of it like drawing a line straight around the equator of a globe. The polarization state moved smoothly and predictably along this trajectory, following a geometric pattern that suggests an underlying physical mechanism at work. The team realized this behavior tells us something important about where the signal comes from. The pattern is consistent with emission that starts out fully linearly polarized at its source, then gets modified as it travels through a birefringent medium. A birefringent medium is material that affects different polarization states in different ways, essentially acting like a filter that transforms the signal as it passes through, and this medium itself appears to be linearly polarized. This kind of transformation signature could become a crucial clue. It gives astronomers a specific technical fingerprint to look for, and it might help narrow down what kind of object is producing these mysterious radio pulses. So the natural next step was to look for this source in other wavelengths. After all, most cosmic objects that emit radio waves also produce some kind of optical or infrared light that telescopes can detect. The team turned to archival surveys, first combing through existing data to see if anything had been recorded at this position. Before they found nothing, not a single detection in any of the standard catalogs. Then they went further. The astronomers requested time on Gemini South, one of the world's premier optical telescopes, to take a targeted look at the source's location. They used an instrument called Flamingos 2, which is specifically designed to see into the near-infrared. This seemed like the right tool for the job, because infrared light can penetrate dust that would otherwise block our view. But again they came up empty. No counterpart, no companion object. Nothing that could tell them what ASKAP J1424 actually is. Part of the challenge here is where this source lives. It sits at a low galactic latitude, meaning it is close to the plane of the Milky Way. In these regions, the disk of our galaxy is thick with interstellar dust that absorbs and scatters light. Astronomers call this effect extinction, and it can dramatically dim or even completely hide objects that lie behind it. So one possibility is that a counterpart does exist, but is simply too faint to see through all that dust. But there is another possibility, and it is more intriguing. The source might genuinely have no optical or infrared counterpart, because it belongs to a class of objects that do not emit much outside of radio wavelengths. This absence of a multi-wavelength detection places tight constraints on what ASKAP J1424 can be. It rules out many ordinary stellar systems and forces astronomers to consider more exotic explanations. Whatever this object is, it is keeping its secrets well hidden. So what is ASKAP J1424? The research team has proposed a leading explanation that points toward a white dwarf binary system. Now, white dwarfs themselves are not mysterious. They are the dense remnants of stars that have exhausted their fuel, packing roughly the mass of our Sun into something the size of Earth. Many white dwarfs also carry intense magnetic fields, sometimes billions of times stronger than Earth's, in a binary system where a white dwarf orbits alongside a companion star. Interesting things can happen. The idea here is that the white dwarf's magnetic axis might intersect with a magnetized wind flowing from its companion. This interaction could create the conditions for regular radio pulses. The timing gets particularly interesting because the pulse period would not simply match the white dwarf's rotation. Instead, it would reflect the beat between the white dwarf spinning on its axis and the two stars orbiting each other. This beat frequency could naturally produce the unusually long 36-minute period we observe. The white dwarf hypothesis has some appeal because it connects ASKAP J1424 to a growing collection of long-period radio transients that astronomers have discovered in recent years. Some of these sources show similar characteristics, and white dwarf binaries have been floated as explanations for others as well. There is a certain economy in reaching for an explanation that fits multiple puzzles. That said, magnetars remain in the conversation. These are neutron stars with extraordinarily powerful magnetic fields capable of producing dramatic outbursts. The problem is that magnetars typically spin much faster than 36 minutes. A slowly rotating magnetar would require some special circumstances to explain. Similarly, isolated magnetic white dwarfs could theoretically produce radio emission, but the evidence for either scenario remains circumstantial at best, without a detected counterpart in optical or infrared wavelengths. These explanations stay in the realm of informed speculation rather than confirmed fact. So where does this mystery go from here? The researchers have made their case for a white dwarf binary system, but the truth is we will not know for certain until we get more data. That is where the second phase of the vast galactic survey comes in. VAST stands for variables and slow transients, and it is specifically designed to catch objects that change over timescales of weeks, months, or even longer. The team plans to point the telescopes back at this region of the sky and watch and wait. What they are really trying to figure out is whether ASKAP J1424 turns on and off in some kind of regular pattern, or whether what we saw was just a one-off event. Think of it this way. If the source is a white dwarf binary pulling material from a companion star, you might expect to see it flare up again and again each time the system reaches the right conditions. That would be an intermittent activity pattern. But if instead the radio burst came from a single random event, like a blob of plasma getting accreted all at once, then it might never happen again, or at least not in any predictable way. Distinguishing between these possibilities matters. It matters because it tells us what kind of engine is powering the emission, and that is what will ultimately confirm or rule out the white dwarf binary theory, or point us towards something else entirely. Either way, ASKAP J1424 has already done something important. It has added another piece to a puzzle that astronomers are just starting to assemble. The population of long-period radio transients is growing, and each new discovery like this one helps refine the picture. We are learning that the universe contains objects we did not expect behaving in ways we do not yet understand, and sometimes the only way forward is to keep watching.